So welcome to the colloquium of the Institute of Physics at the EPFL. So today we have the pleasure of having Brian Swingle from Brande. So Brian did his PhD at MIT with Xiaogang Wen, and then he did postdocs at Harvard and Stanford. And is really one of the pioneers in this emerging field between quantum information and gravity. In fact, I remember when I was a postdoc, I remember Brian was a PhD student and he was already famous. He came up with this, pointed out this connection between the entanglement structure in tensor networks and the holographic nature of gravity that string theories discussed. Okay, so he continues to push this topic and this subject. So Brian, please, the screen is yours.
Great, thank you very much for that very kind introduction. Thank you for the invitation. It's a pleasure to be here with you, virtually at least, and to talk with many of you, and hopefully we can visit in person again someday soon. So yeah, I'm going to talk today about just part of the story. It's a big story, but a part of the story of this intersection, this emerging intersection between quantum information and gravity, sort of told from the point of view of black holes as quantum information processors, and actually in some sense extreme quantum information processors, in that they saturate certain bounds and tend to do things very well in a certain precise sense. Happy to defer to your local custom, but if you want to interrupt during the talk for questions, feel free to do so. I'm totally fine with that. And yeah, I'll tell you about work spanning many years supported by these different bodies here. And yeah, let's get started. So I want to start from the quantum information side of things, because my background is really many body physics and solid state strongly correlated physics. So I want to think about it in terms of frontiers to start. So you're probably familiar with various kinds of frontiers in physics. For example, what you might call the size frontier, looking for new physics at very large distances, or at very long time. So you're looking back in time towards the Big Bang, trying to understand physics of the very early universe. There's also the energy frontier, new physics at high energy. So think about the LHC, trying to collide particles at ever higher energies to reveal fundamental interactions. There's also the intensity frontier, looking for new physics by conducting many experiments. So to look for very rare events. This can also give you insight into physics, the new physics. And from my point of view, there's another frontier, which is what you might call the entanglement or complexity frontier, which is looking for new physics at high complexity and with macroscopic quantum phenomena. And this frontier is associated with lots of different parts of physics. I would say the study of quantum materials, even non-complex quote unquote quantum materials are in this frontier. All of the work of quantum simulators and quantum computers also aligns with this frontier. And then of course, as I'll talk about in this talk, there are various kinds of extreme situations, extreme conditions, perhaps in the very early universe, perhaps associated with black holes, where you might also expect some of this high entanglement, high complexity physics to be relevant. And I always like to mention, at least, it's always possible that when we look for the quantum physics of millions or trillions or more of particles, we'll find something beyond quantum mechanics. Maybe quantum mechanics breaks down at some scale. That would be very interesting. We don't have any evidence for that yet, but it's always something to keep in the back of our minds. And so I want to think about this entanglement complexity frontier, and I want to argue that, besides giving you a small glimpse of it, that the physics of black holes actually has a lot to do with this entanglement complexity frontier. So here's a picture of the universe, the cosmic microwave background. Let me give you a sense of what this frontier is about. Suppose we filled this whole universe with hard drives.
So we're not seeing, I'm still seeing the frontier slide, Brian.
Oh, really? Let's see, can you see the picture now?
Yes, now, yes.
Okay. You can see the next one?
No, still in CMB.
Let's see here.
Sometimes if you kick out the full screen view, it helps.
share again.
Could it be because you are not signed in on Office?
I don't know. I mean, it's usually not a problem, but is that, you see the transitions now?
Yes.
Okay, let's go with it and see. Let me know if it blanks out again. So let me try to explain this frontier a little bit. So here's the universe. Suppose we fill this universe with hard drives. They fill a whole Hubble volume with the best current hard drive. This would store about 10 to the 97 bits of information, which is not even enough information, not enough space to write down the wave function of even 300 quantum spins. So you have 300 spins, you have 2 to the 300 quantum amplitudes for the complete wave function. And even if you just use the entire universe to write that down, you couldn't do it. So the first point here is that there is somehow an incredible richness inherent in this quantum many-body Hilbert space, the space of quantum states. There's a lot of room. So much room that you can't possibly hope to describe the physics by just writing down the wave function. You need a better way of thinking about the physics of your system. And this is, of course, quite reasonable. Experimentalists don't tell you the complete many-body wave function. They measure, quote unquote, simple observables like magnetization or heat capacity or so forth. And so somehow part of the challenges of this frontier is to translate this vast kind of Hilbert space of possibilities into the concrete things we see in experiment, and also to understand what new possibilities are afforded that we have not yet seen and how we can probe. Now, in my own background, this vast potential complexity gives rise to quite a lot of exciting phenomena. I grew up hearing about the fractional quantum Hall effect shown on the left, where you have a two-dimensional electron gas exposed to a strong magnetic field. And then you can look at the Hall conductivity, that essentially you pass a current in the x direction and measure the voltage in the y direction. And what you can see is this series of quantized plateaus. So this line here is the Hall resistance, and you see this quantization. This flat line here is the single field Landau level. But also you have these 1/3 plateau here, which is some kind of intrinsically strongly interacting state of matter. And then you also have the famous high temperature superconductivity, where you have a superconducting region here at low temperature, but all kinds of other exotic phases, strange metal we don't understand, pseudo gap phase, some kind of other phase we don't understand, you know, strongly correlated magnetism over here, lots of exotic things. And of course, this was known for many years. But as I was growing up, we were starting to re-examine these phenomena from the point of view of this entanglement complexity frontier, viewing these as highly entangled, highly correlated, non-trivial phases of matter. Right? And these rich set of phases here that we get in fractional Hall effect and high temperature superconductivity are only the start of the story. In a sense, you can view all this interesting complexity of quantum many-body physics, of quantum material science, as different kinds of manifestations of highly entangled quantum mechanical many-body systems. Taken to one extreme, you can try to actually use this to do interesting computations. You can leverage the power of many-body quantum physics to try to compute in a way that's not possible classically. This is the subject of quantum computation. We can, of course, use quantum computers for all kinds of things. We can use it to simulate quantum many-body systems to learn more about these things we've been studying for a long time. We can try to solve problems of relevance to society. We can even try to simulate high energy physics, and I'll come back to this at the very end. This is kind of the dream here, though, of the fully controllable, fully coherent many-body system where we can really choreograph the collective quantum effects however we like. And that's one long-term vision of this entanglement complexity frontier. That's all great, but what about gravity? Okay. Now, just to remind you, I'm sure you all know, but gravity, our current best description of gravity is that viewing it as an emergent phenomenon, something which comes from the physics of a dynamical space-time geometry described by the general theory of relativity. And this theory, like the quantum theory I was talking about before, is enormously successful. It's discussed gravitational waves, lensing, corrections to orbits, black holes, and much, much, much else. So it's an incredibly precise theory, incredibly successful theory. But there are well-known challenges to combining quantum physics and GR. This is what's called the problem of quantum gravity. So you have these kind of two very successful theories, if you like, quantum field theory, which includes standard model and all the physics of our everyday lives. And you have this theory of gravity, which is also extremely successful. But merging the two of them presents challenges. And one of the places that that challenge is most prominent is in the context of black holes. So on the right here, I'm showing you this now famous picture of LIGO data from their first detection of gravitational waves from a black hole merger. So here's the facilities at the top. I had the pleasure of visiting the Hanford facility many years ago. And even then it was amazing. They could show you tumbleweeds hitting the side of the beam pipe, the traffic in LA in the morning and so forth. So it's an amazing instrument. And with this amazing instrument, they were able to detect gravitational waves emitted from a merger of two black holes. So this is the best evidence yet, the most direct evidence yet of this black hole event, of these extreme black holes and the gravitational waves from them. And what's the problem with these black holes? Well, here now I'm showing you a picture of the space-time around the black hole. So in the x direction is space and vertically is time. And this is a black hole formed by collapse. So this line is meant to indicate some shell of collapsing matter. This jagged line in the center is the singularity, and this dashed line is something called the event horizon. I'll explain what happens at the event horizon in a second. But first, let's look far away. So far away from the black hole, space-time looks more or less like flat space. And you have light cones, these little cones here, which tell you that if you're at this point at the center of the light cone, then you can move to the future, but you can't move in space, right? And the maximum possible speed is the speed of light, which is this slope here. And what happens near the black hole is that these light cones get increasingly tilted. The gravitational pull of the black hole makes it harder and harder for you to escape out of the pull of this black hole. And eventually, at a certain point, the light cone tilts so much that even if you're going at the speed of light, you're actually still heading towards the singularity. You can no longer escape to infinity. So this event horizon is like a place where gravity is so strong that you can no longer escape to infinity. And so the black hole is really distorting space-time in a sort of qualitatively new way. And the basic issue in this context is that, okay, suppose I have some information outside, I throw the information into the black hole, so it passes through the event horizon. Now it seems to be stuck inside. Why is that an issue? Well, one of the basic principles of quantum physics is unitarity, that if you evolve system forward in time, you can also evolve it backwards in time. Or if you like, the time evolution is reversible. Or another way of saying is that information is never really lost. But from this point of view, it looks like information you throw into the black hole gets stuck inside. Now we know that black holes do radiate, but that radiation looks quite thermal. So it looks like you're throwing in structured information, you're getting out unstructured thermal radiation out. And this is a problem because it looks like, from some point of view, that information is being lost or converted to some featureless noise in some sense. Now, I'm not claiming this is really a paradox. I think we know how to understand at least part of this story now, in part through the technology that I'll describe a little bit. But you can see how it's an issue. Okay, so you have this beautiful structure, quantum information, quantum many-body physics, quantum field theory, but rooted in some very basic principles, and those principles seem to have some conflict with the structure of black holes. And that's just one of the examples of tension between gravity and quantum mechanics. But we have a very good reason to think that this tension is not really there, or there is a tension, but it has a resolution, and that resolution is interesting. And that's because we have at least one model of a quantum theory of gravity where we have a gravitational system and we have, in principle, we think, a complete microscopic quantum mechanical description of that system. This goes by the name of the anti-de Sitter space conformal field theory duality, or ADS-CFT, or holographic duality for short. And the idea illustrated in this cartoon is as follows. So on the left, you have these red degrees of freedom. This is the conformal field theory degrees of freedom. Think of this as just a complicated quantum system, complicated quantum many-body system. There's field degrees of freedom here. In this case, it lives in one space, that's the ring, and one time, that's the vertical direction, degrees of freedom. And there's no gravity here, no explicit gravity. So Newton's constant is turned off. And this is supposed to be equivalent to, exactly equivalent to a theory of gravity living in the bulk in the interior of these rings, which I've colored in blue, which has at least one more dimension. I'm of course glossing over a lot of details, but this is the basic idea. And the important thing about this blue region is that Newton's constant is turned on there. So you have dynamical gravity in that region. So if you like, the boundary is fixed, it's rigid, but the interior is some fluctuating dynamical geometry in which gravity lives. Right? And the claim of Maldacena, developed over many years since then by many people, is that these two systems in the right situation can be completely equivalent. Okay. And in this context then, we can revisit black holes. There's also black holes in a de Sitter space. And what we arrived at by thinking through the physics of black holes in this context is that the way to think about black holes is really actually as a kind of chaotic quantum mini-body system. That all the puzzles we were talking about, all the confusing and interesting features can be reconciled if we think of them in this way. And that's going to be the subject of the rest of my talk. But let me set the stage here. So first of all, why do they have degrees of freedom at all? A black hole is just a configuration of the metric, right? But actually we've known since the early days that by Bekenstein and Hawking that black hole is associated with some entropy. So you take the area of the horizon of the black hole. I already explained to you what the horizon was. You take Newton's constant and Planck's constant. I've suppressed the speed of light here, just put that to 1, but I've kept these two explicit. And Bekenstein and Hawking said that this black hole has actually an entropy proportional to the area divided by g Newton. And in the semi-classical limit, when g Newton is very small, which is like our world, for a big black hole, this entropy is very large. So first of all, we have a very large number of degrees of freedom. That's the first takeaway. Okay. The second takeaway is that these degrees of freedom interact and actually relax. They exhibit phenomena that we would expect of a relaxing quantum many-body system. If you look at this LIGO data here again, this is the in spiral, this is the merger, and then this late time physics here is called the ring down. This is actually this pair of black holes merging to one and then approaching equilibrium at late times, approaching a static or a steady state solution. And if you look at your simplest kind of black holes and you ask general relativity to compute how does this black hole decay to its equilibrium value, you make a little ripple and you see how it decays. You get some time scale for that decay. If you then take the entropy and energy relationship and use it to compute a temperature, what you find is that the time scale associated with that decay in units of the temperature is h bar over the temperature. So this is a very basic time in thermal quantum systems, the time set just by Planck's constant and the temperature. I've suppressed Boltzmann's constant again. This is some kind of very basic time scale that you see in a wide variety of contexts. And it's associated with kind of the fastest possible, in some sense, relaxation that you can have in a quantum system, in a thermal quantum system. So to summarize, black holes have a large set of states. They have a big entropy, and they have some dynamics. They relax to equilibrium on a relatively short time scale, controlled by their temperature and by Planck's constant. So now I want to explain a little bit of how we think about these things more precisely in this picture. So let's start out from empty space. In empty space, this is anti-de Sitter space. This is a spatial slice of it. This is a hyperbolic space, so it's not like our usual flat space. In this space, all the fish have the same size. They're drawn in this interesting way in this nice print from Escher. But in principle, all the fish have the same size. That's the hyperbolic metric. And you can see there's like a boundary which is in some sense infinitely far away. The fish are getting smaller and smaller and smaller at the boundary. Right? So this is what a spatial slice of this can looks like.
Can I ask?
And the first thing you can ask, okay, how do I understand what this ground state is, what this empty space is from the point of view of the boundary degrees of freedom? And the idea is, okay, it's empty space, there's no excitation, so it should correspond to the ground state of my boundary system. Okay, great. But what precisely does that mean? Well, I can think about the ground state as having some representation in terms of a recipe to create the state. So I have this complicated state in this many-body Hilbert space. And I said it was important for us to have a way to understand how to describe that state in simpler terms. And one way to do that is in terms of a recipe, which tells you how to build that state from nothing. Or if you like, instead, how to disassemble that state from its complexity. And that's what this right side picture is trying to convey in a very schematic fashion. This is what we call a tensor network. If you like, the legs at the outside edge are the physical degrees of freedom. Each leg corresponds to, say, a spin half or a qubit or something like that, some degree of freedom. The details are not important. And each of the little blobs here is a tensor, which connects either to physical degrees of freedom or to some other internal degrees of freedom. And the idea is this picture here, this tensor network, is quite literally, in this case, a recipe or a picture for how to create the quantum state of the boundary in terms of elementary operations or components, these tensors. So instead of telling you the complete wave function amplitudes of the universe, of this state, what I tell you is instead a recipe for creating that quantum state. And that provides a more efficient way of talking about it.
Brian, I think there is a question by Marco Menere. If you want to
please.
Questions now.
Yeah, thanks. I wanted to ask about the previous slide, actually.
Sure.
Could you just give, please, an example of what's the typical scale of relaxation time instead for some ordinary quantum system, which is not a black hole? Why is it that much longer?
So like yeah, happy to. So the simplest example, like if you think about, say, a metal, I'm not sure what your background is. So if this example means nothing to you, you can let me know and I can change a different one. But think about a metal, right? So this is electrons at finite density with some background potential and scattering off of each other. And because of the Pauli exclusion principle, it turns out that the scattering of these electrons goes like temperature squared divided by some characteristic energy, the Fermi energy. Now, that's valid in the regime where the electrons are relatively well-defined quasi-particles compared to the Fermi energy. So you can imagine you heat those particles up or lower the Fermi energy sufficiently so that the temperature is comparable to the Fermi energy. At that point, you'd lose a notion of quasi-particle altogether. And then you'd predict that the scattering rate would be proportional to just the temperature itself because the temperature is of order of the Fermi energy, right? So that's one example where you can see that sort of pushing the energy scales close together, or if you like, turning up the interactions in some sense, you can reach a regime where you start to lose control of the theory where the scattering time is roughly of this scale, right? Now, I'm not claiming that's like the complete story there, but that gives you just a sense of how to see this kind of time scale emerging from something perhaps more familiar.
But so in any theory which doesn't have a scale, say a conformal field theory, etc., this would be the scaling then.
That's right. You know, if you have a scaleless theory, like a quantum critical point, then you would typically expect this is the scale that sets the scattering of your particles.
So even if it's not holographic, so this is not a special feature of black holes, it's a feature of massless system. Okay, thank you.
Yeah, like, you know, you can take your, you know, ON quantum magnet or something like that. At large n, there's a 1/n suppression at this scale, or there's a factor of n here. But if you set n equals 1, just, you know, roughly speaking, you would get this time scale for the scattering. Right.
Thanks.
Okay. Yeah, so what this really is really a picture of the quantum state and a precise recipe for making it. And this recipe has some features. So for example, one of the ways that ADS-CFT makes contact between the boundary and the bulk is the following rule for computing entropies in the boundary. So here I'm talking about something called the von Neumann entropy. The details are not, they're important, but I don't have them to tell you about them. But this is a way of assigning entropy to subsystems, where you look at the reduced density matrix of the subsystem and you compute its entropy as the von Neumann entropy. And one entry in the ADS-CFT dictionary, so-called, which is called the Ryu-Takanagi formula, so that the entropy of this boundary region is equal to the area of a curve in the bulk that has minimum area. So you look for all the curves that end in the same point on the boundaries. You minimize over them, you find the one in the minimum area. And the minimal area in Planck units, that's this combination h bar g Newton, is equal to the entropy of that system. Okay. But from the point of view of the network we have, the network representation, this makes perfect sense. If I want to know the entropy of this region, well, we know that entanglement is generated by interactions between particles, right? Particles that have not interacted can't have any entanglement, but we can generate entanglement by causing interactions between them. So each of these lines is sort of like an elementary little bit of interaction between some nodes in this network. And so somehow the number of lines that we cut via this surface provides a bound then on the amount of entanglement that can be present in this boundary region. And then if we minimize the number of lines we cut, that would be the best possible bound, right? So this is some point that I made in my first paper on the subject. But then we can also go on and design tensor networks, that's these kind of networks here, which realize this exactly. Okay. And so this network picture is a very natural then representation of what's happening here. We say that the space-time itself is literally just a picture of the quantum circuit, the quantum procedure, the quantum recipe that prepares the ground state. And from that point of view, it's very natural that you'd have something like this Ryutakyanagi formula, where entropies on the boundary are related to curves in the bulk. We can do a similar kind of story for black holes. Instead of preparing the ground state, now we can try to prepare a thermal state. That thermal state should have some entropy. So now if you think about it a little bit, when you turn on some thermal perturbation, you're going to introduce typically a correlation length. So things won't be correlated at all scales anymore. And there'll be some maximum degree of correlation, which is associated with the fact that you now have a maximum depth into the black hole. And now these legs in the interior, what's happening with them, now we would inject some entropy into them, which is like the entropy of the black hole. And then that entropy is embedded in some way into the Hilbert space of the macroscopic theory via this network. But the formula still makes sense for entanglement, for example, for entropy. We can now look at the entropy of this region, and we'll have some contribution from the ADS-CFT point of view, which is associated with the network itself, and some contribution that's roughly associated with the black hole, which is counting the entropy of the black hole. And you have the same kind of picture in the network point of view. And so what this is saying now is that in a finite temperature state, now if you ask for the entropy of some region, you have some contribution, which is related to entanglement, if you like, between degrees of freedom, and some contribution which is coming from the thermal entropy of the black hole, which is this near horizon piece. And so actually this is one of the entries in the dictionary that says the entropy of the black hole is just the entropy of the whole space-time. Because if you take this dash curve all the way around, then this red solid curve can disconnect and just wrap the black hole. And so you just predict that the entropy of the whole system is the entropy of the black hole. So you think of the Ryutakyanagi formula as like a generalization of black hole entropy.
Can I ask a question as well?
Yes, please.
Sorry, just to clarify, so what should I think of these nodes in this tensor network as being or as representing?
Well, I'm being quite schematic here, but you can think of them as being quantum gates. So whenever you have, say, 2 legs in, 2 legs out, think of that as a unitary gate. And when you have something like 2 legs out and 1 leg in, you can think about there being an extra state you're inserting like some reference configuration here, like inserting a 0 state. So tensor networks are a big set of things. They're not all of this form. It's generally speaking just some way of representing this complicated many-body state via some simple ingredients. But for the kinds of things I'm talking about here, you can actually think of them as composed of unitary tensors that you could in principle implement. If you had complete control over the quantum system, you could actually implement these as physical dynamics, which generate the entanglement necessary to make this complete many-body state.
May I follow up on this question very briefly? So, I mean, perhaps this is due to my ignorance on this holographic correspondence, but I mean, if this is a tensor network, it's a 3-tensor network essentially, then we know from tensor network theory that they don't represent volume laws. They represent entanglement only in a limited way because they express area laws. So essentially, in terms of complexity, they are not as exponential as the exponential complexity that you mentioned in the first slide with the example of the hard disks. So how can this model be realistic for describing the reality of quantum of our space? We know it will not represent its complexity.
Yeah, it's a great question. So you know, as you alluded to, what the tensor network can represent depends on its geometry. And here you said it's a tree tensor network. I would say it's not quite a tree because it has this sort of lateral connections.
Sure.
So actually this can represent, what this tensor network gives you is a boundary state whose entanglement is controlled by the area of this higher dimensional geometry, right? And if we choose a different geometry, then we can choose more, we can have a more expressive state. So you're absolutely right. To make a tensor network that covers every possible state requires either very large dimension for these lines, many degrees of freedom, or a very complicated tensor network.
Okay.
And that's true. However, it turns out, at least from the point of view of ADS-CFT, or from the point of view of many kinds of materials questions, we don't actually need all that complexity. That's another part of the story that I haven't focused on. But like these ground states here, they're complex, but actually not so complex, so that we can actually capture them effectively in some cases with these tensor networks, or at least we think we can. That's a very important question. Yeah.
Thank you.
All right. So let me go back here now. We've understood something very schematically about how to make this space. If I sort of fix time and go across like here up to the event horizon, we've kind of understood how this space works from a quantum information tensor network point of view at late time. I was thinking about the black hole in equilibrium, so I'm gone way past the collapse and looking at here what's in quasi-equilibrium. But now let's go further and let's ask about these bending light cones. How can I understand that from the point of view of information and the boundary? Okay. To think about that, we need to think about speed limits. So here's the ultimate speed limit, speed of light, and I think kilometers per hour, I forget. But I adjusted the stop sign, I mean the speed limit sign to be your native speed limit sign or something close to it. But you're probably more familiar with something like this. So you're familiar in life with the speed limits that are imposed upon us besides the fundamental speed limit set by light. And we can ask, where do these speed limits come from? Because this might be reasonable to ask in the context of ADS-CFT, because if the geometry is emerging from entanglement, from correlation, well, then maybe the space-time structure emerges too. And so we can ask how the speed limit actually emerges from the dynamics of the boundary system. And what will be relevant for us is the kinds of speed limits that emerge when you have strong interaction. So here's a person experiencing an emergent speed limit due to the coupling of this gas of sheep. We're going to be interested in a similar kind of thing, but where you have strongly interacting quantum particles. Okay. And the idea here is to think about a notion of speed associated with information propagation. We can try to measure speeds in various ways. In a weakly coupled system, we can send information, using electromagnetic waves, for example. But strongly coupled systems with strong interactions don't typically transmit information in any kind of simple, accessible form. If you dropped your information into the quark gluon plasma, good luck getting it out again. We think it's there in principle, but it's not easily accessible at later time. And one nice thought experiment you can use to track how information is spreading is the following. You can imagine a reference system that you don't do anything to. You just set it aside. Nothing happens to its dynamics. And at time zero, you entangle this reference system with, say, one spin or one qubit of your quantum system. Then you set the reference aside. The entanglement is there, but nothing happens to the reference. Let the system evolve. And you can ask the question, how big of a region do I need to have access to recover this initial entanglement? It turns out that in many cases, the size of that region grows with time ballistically, and that defines an information speed VI. And what I'm going to claim is that this information speed is actually related to the emergence of the speed of light in the bulk. So let me explain that to you now. To do so, I need to take a little quick detour to talk about quantum chaos. how do we characterize chaos in quantum mechanical systems? This is actually a very complicated and interesting subject, but I want to present one characteristic feature, which is what I call the quantum butterfly effect. And the idea of this is the following. You can imagine comparing two situations, one where you run time forward, that's the red line, the orange line. And then if you immediately run time backwards, then because of unitarity, you just go back to where you came from, right? It's like you rewind the tape and you get back to the start. But if time runs forward, then I make a small perturbation and then time runs backwards. Initially, the forward backwards will mostly cancel out, but this perturbation will eventually manifest and cause the system at late time to end up in a very different place. So this is like an abstract way of thinking about some kind of butterfly effect where the wing flap of the butterfly is this little perturbation here. So imagine I just flip one quantum spin. That's a tiny perturbation, the smallest perturbation I can imagine. How does that single flip affect the system at later time? If you like another analogy, it's sort of like assembling some impossible IKEA furniture. I hope you've all had the pleasure of doing this at some point in your life. It's like you're trying to make this cabinet here, this container for books or something, and you get to the 34th and final step, and you realize you have this wonderful cabinet, but there's a screw left over. And you're like, okay, where did this screw go? Well, you realize you missed a screw in step 2. So basically, the only thing you can do at this point, unless you're very skilled, is like unbuild the whole cabinet back to step 2, put the screw in, and then rebuild the cabinet. Right? That's how you can fix it. That's this butterfly effect. On the other hand, you can say this looks more or less cabinet-like, whether it has a screw or not. It's pretty stable. And that's a picture of thermalization, right? The details don't matter. But in principle, you have a very different microscopic state, whether the screw is there or not. Let's see how this plays out. So here's a space-time diagram. Here's space on the x-axis and time vertically again. Each of these lines is like a single spin or a single qubit. And I can describe the forward interaction by the forward evolution by a set of interactions of this type. So I pair the evens and the odds in this different layers. This is just a schematic of time evolution. And I have backwards. And when I don't do any perturbation, well, the forward and backwards just cancel, right? Because they're inverses of each other. It's just unitary evolution, forward evolution, then backward evolution, nothing happens. But if now I insert a fly in the ointment, or I put a butterfly in here, which flaps its wing, which perturbs one spin, at first, most of the gates cancel, most of the interactions cancel, and there's only a little bit of residual non-cancellation. But now the blockage associated with this perturbation is spread from one site to 2 sites. Right? And I keep following this procedure. I cancel more. Most still cancel, but the blockage is growing. The perturbation is growing. I keep doing, and I keep canceling, and the blockage keeps growing. And what you can see is that this perturbation, which is initially on just one site, is actually growing in space as a function of time. And the picture suggests that it actually grows with some kind of effective light cone. Okay. How can we probe this? Well, we can take this structure and we can ask, okay, if I put another probe operator in there, this little V, this little red V, I can test whether it commutes or fails to commute with this big blue structure. So if I put it far enough away, it just commutes. I can move the V from the top to the bottom of the diagram. That means it commutes. If they fail to commute, if it's inside here, then it won't be able to pass from the top to the bottom. And the failure, the degree of failure to commute, gives me a measure of how far this thing is spread. Just to be technical, we use this particular measure. So this is the commutator. W is the growing wing flap, V is the probe. You might try to look at this just by taking the expectation value of this commutator. That turns out not to work because this is just related to linear response of our system. And when you have a chaotic thermalizing system, you ping it, it loses memory of its initial condition. And so this response just goes to 0. So we needed to look at something a little bit better. And the next simplest thing is to look at the square of this object. So now this is a positive definite operator inside here. It can't have the cancellations that cause this to 0 out. And we can take its expectation value and look at it as a function of time. What do we see? Well, if I plot at fixed time, this commutator versus R, you see a region where the effect of the butterfly is strong and then a crossover to a region where the effect of the butterfly is weak. Right? If I instead look in space and time and plot the contours of constant commutator, what you'll see is that large space and time, they look like straight lines, and the slope of that line is what I call the butterfly speed. So it's the speed of spreading of the effect of this local perturbation. Now we can compute this in the context of ADS-CFT. That's a calculation done by Schenker and Stanford and Kataev in some years ago now. And what you find, look at this lower panel here, is that for the black hole, which is corresponding to some thermal state, this commutator has the structure of an exponentially growing in time piece, an exponentially decaying in space piece, and some suppression related to the entropy density of the black hole. This exponentially growing piece is like a Lyapunov exponent. It's like an exponent that you know from the classical theory of chaos controls the deviation trajectories. There is a precise notion of this, but I won't go into it here. And then the exponentially decaying in space piece is such that the level sets of this function in space-time, the contours of constant commutator, are indeed straight lines with speed set by the butterfly speed. So this is something you can compute in ADS-CFT. This exponentially growing piece has to do with falling towards the black hole and getting exponentially large energy as a function of time, right? As you fall in, the gravitational attraction pulls you more and more, you accelerate. This other part has to do with the spreading of perturbations on the horizon of the black hole. Okay, so this makes sense. I just want to flash that we can also compute this in the context of spin chains using tensor network methods. So another kind of technology that I talked about. I don't want to dwell on this because it's sort of orthogonal, but just these cartoons I showed you, we can really flesh them out and make them very precise and actually calculate in large size systems using tensor network methods. Okay, so I'm happy to talk more about that in the Q&A if you're interested. But let me go back to the central story of black holes. So we have this picture. We have chaos. We have the growth of perturbations. And I said that you can see this in ADS-CFT as well. What does this have to do with our initial information spreading story? Well, let me tell you how to track information in ADS-CFT. Let's go back to the thought experiment I started with, which was I take a reference and I entangle it with a particle in my system. In ADS-CFT, I can imagine that's just a particle that's starting out at the edge of space. So it's a particle in the CFT, it's simple, and it sits right near the edge of the bulk spacetime. That's what the duality tells me. And I can entangle these two particles, right? And then I put the reference away, and I let the CFT, or this bulk spacetime, evolve in time. And what's going to happen is this particle is going to fall in. It's going to fall towards the black hole, pulled by gravity. And I can ask the question, okay, what region do I need to have access to recover that particle? And now I'm just going to tell you a rule. This is a rule that follows from the Ryu-Takanagi formula and its generalizations. So I won't explain it, but I'll just quote the rule to you. The rule says you look for regions on the boundary such that the minimal curve here, this dashed line, contains that particle inside of it. And if it contains that particle inside of its minimal curve region, then that region on the boundary can access that particle. Right. So if the particle is inside the minimal curve region, called the entanglement wedge, then that region on the boundary knows about the particle. And if the particle in the bulk is not inside that entanglement wedge, then the boundary region cannot recover it. It does not know about it. So let's ask how this works for the black hole. The particle, as I said, starts near the edge. It starts to fall in. And as it falls in, I need larger and larger regions on the boundary to capture this particle as it comes closer and closer to the horizon of the black hole. It never quite passes the horizon as far as the boundary time is observed, but it gets closer and closer and closer. And eventually, at very late time, it's falling with very nearly the speed of light. It's been uniformly accelerated for a very long time, so it's just basically going the speed of light. And I can ask, okay, as this particle is falling in now, essentially at the speed of light near the horizon, how big of a region do I need on the boundary? How fast does it have to grow with time such that it just contains this infalling particle? So I just have access to the entanglement. And you could do that calculation, first done by Stanford and Mazet, and then generalized by my collaborators and I. And what you find in the simplest case is that the speed on the boundary is just the butterfly speed. In particular, this butterfly speed for many cases of interest is much less than the boundary speed of light. Right? So in other words, if information on the boundary is propagating at the maximum possible velocity allowed by the laws of nature on the boundary, things in the bulk would actually be going faster than the speed of light. So it's actually the strong interactions on the boundary, the slowing down of information coming from those strong interactions, the emergence of a speed limit, which is dual to the fact that there is this bulk speed of light speed limit in the black hole spacetime. So to come back to this picture, now we understand not just how to build the space itself from entanglement using this tensor network, but we also understand why the light cones are tipping over and why things are slowing down near the horizon. It has a nice picture in terms of the chaotic dynamics of the boundary far away, leading to an emergent kind of speed limit that's manifested in the bulk as the bulk speed of light. So the dynamics of this space-time and the structure of this space-time are actually all, in some precise sense, encoding the structure of entanglement and the dynamics of entanglement information in the boundary degrees of freedom. So not only are black holes compatible with entanglement and quantum information, etc., they are sort of closely linked to it. They actually give us a very simple manifestation of all of those complicated phenomena in terms of this bulk picture. Okay.
May I ask a question?
Please.
Just a silly question, perhaps. I mean, this butterfly speed at the boundary, is it just the speed of sound of the dual thermal medium, or is something else?
It's not. So
no,
for
much less than the speed of sound, you're saying.
Yeah, for CFT2 for 1+1, it's the same. So the speed of sound is the speed of light, which is also the speed of butterflies. In higher dimensions, the speed of light, then the speed of butterfly, then the speed of sound is lower, right?
Okay.
So this does not correspond to a propagating like coherent mode. It's actually something that moves faster.
Okay, thank you.
Yeah.
Can I ask another question about this
Please.
speed? So before, when you showed the structure of the double commutator, it had exponential, at least, I mean, there was a wiggle, but it had exponential tails, which would be non-zero, exponentially small tails, which would be non-zero even after, I mean, even for distances bigger than the speed of light. So when the thing actually has to be zero. So what, from the point of view of gravity, what are the corrections that restore causality?
Well, so there's I want to distinguish two things. So there's the speed of light in the bulk, and then how you connect that to this boundary butterfly speed. So in the bulk, you can, I don't want to say the speed of light is absolute, but in some sense, it's fairly robust. And this like bleed over can be associated with the fact that the bulk particle has a wave function, for example, or the mapping between the bulk particle and the boundary region is a little bit fuzzy, rather than the bulk speed of light being violated in some sense. So it's like the mapping is a little bit fuzzy rather than the speed is being violated. Does that make sense?
Okay, but is there some piece of the dictionary, the SCFT, like non-perturbative corrections, etc., that make this this formula compatible with causality? I mean, could you replace an equal sign to the wiggle in the formula you had about C?
With this, which formula? This here?
Before. One more, I think. Yeah, actually, yeah, top right or here bottom, yeah.
Yeah. Yeah, this wiggle is just because there are higher order corrections here. That's the reason why I put the wiggle there. But
I mean, I just mean that I cannot take x arbitrarily large, right? And this formula be valid at fixed time, because then it would be non-zero.
That's right. So you know, in this context, this particle still fall under the speed of light, essentially, but the way you translate, the way you would compute the commutator very far away is not directly related to this simple calculation in terms of the geometry anymore. Like there's a more complicated relation. So the thing which is breaking is not the speed of light, but just the relationship between this infalling particle and the boundary region.
Okay, thanks.
Yeah. Okay, so let me wrap up here. It's 50 minutes now. So what I told you, you probably heard this before from other speakers, but I reminded you that ADS-CFT provides one model of quantum gravity. And I tried to convey at a very high level that at least within ADS-CFT, quantum information and black holes are not really antagonistic at all. They're actually tightly linked. In fact, all these interesting black hole phenomena have manifestations in terms of quantum information. There's a whole bunch of topics I did not have time to talk about, including entanglement and wormholes. I didn't talk about behind the horizon and complexity, but that's something we understand reasonably well now. We can talk about evaporating black holes and actually address how the information comes out. That's a very recent development. We can also talk about how other kinds of measures of quantum chaos, like random matrix-like energy levels, how those emerge from gravity. These are all developments that have been taking place in the last couple of years. And so there's really quite a lot of exciting progress in the context of these particular kind of black holes, where we see how the quantum information is, again, not antagonistic in any way, but actually just is kind of making the whole thing work. But there's also quite a lot of questions. So for example, I didn't say anything about supersymmetry or the cosmological constant. I just assumed I was in anti-de Sitter space and discussed things from that point of view. We'd love for quantum information or many body physics ideas to say something about these problems, but so far it hasn't made a real impact. Some of the big frontiers are thinking about cosmology and other kinds of spaces. So unfortunately, we don't live in anti-de Sitter space, so this is not really a theory of gravity in our universe. But we can hope that some of these ideas that have been developed, these quantum information ideas over the last, say, 10 or 15 years, might be able to shed new light on these old difficult problems of formulating quantum gravity and cosmological spacetimes for dealing with the Big Bang, etc. That's something that we're thinking about right now actively in my group, and a lot of other people in the community are also thinking about. And then one more prospect that I want to mention, which I'm personally very excited about, is the idea that once we have this connection between quantum information and black holes, or quantum information and quantum gravity, we could actually then in principle use quantum simulators or quantum computers to study gravity in the lab by simulating these holographic models in interesting or uncontrolled regimes. Right? So of course, this is not going to tell us everything we want to know about the gravitational field in our naturally occurring universe, but the black holes I talked about are not so different, we think, from the black holes that occur in flat space. They have some important differences, but many of the properties that I talked about, chaos, entropy, etc., are still there. And so we can very much hope to learn about how quantum gravity works in our universe by conducting these kinds of simulated experiments in other kinds of universes, but in regimes where we can't control the theory, right? So there's plenty of questions we can't answer in ADS-CFT that we'd like to. And we can actually imagine in the not too distant future that quantum experiments using computers or simulators can help us answer these questions. So it's, if you like, a new non-perturbative tool for dealing with quantum gravity. We can carry out simulated experiments that would not be possible in the real universe for hundreds or thousands of years by using these power of holography to access this physics in a different way. So that to me is a very exciting connection. I didn't get to talk much about experiments here, but this is something that we're actively thinking about as well. And I think has a very exciting future as quantum technology continues to develop. So with that, I'll say thanks and happy to take further questions.
Thank you. Thank you very much, Brian.
Thank you.
Okay, so maybe it's better if you raise your hands. We can go in order. Go ahead, Tatsuya.
Thank you very much for the very interesting talk. In fact, it's a really bit stupid questions, but the way how you introduce the speed of light, it looks like in the end, then the speed of light is not really constant, but fluctuating sort of velocities, locally fluctuating, because it's not well-defined boundary in the end. There's some quantum fluctuation around the boundary, which introduces the speed of light to fluctuate.
Yeah. I would say it more like this. It's like the speed, the effective speed on the boundary is state dependent.
Yeah.
So suppose you're in the ground state. There's no excitations. If you make a perturbation, that perturbation will travel at the speed of light. The boundary is just some ordinary Lorentz invariant quantum field theory of some type. So it has a speed of light, and perturbations will just travel there. And actually that works. If you do the calculation, if you do the same calculation, but without the black hole, just in an empty space, you'll find that the region you need to include the particle is growing at the boundary at the speed of light. So that works. But then if you change the state, if you introduce these other degrees of freedom that are kind of, in this case, effectively slow your energy down, your information down, then the bulk description changes. The geometry here changes to this black hole geometry, which indeed has a different causal structure. And that's reflected in the change in the butterfly speed from the speed of light to this finite speed less than the speed of light on the boundary. So it's really, I would say it's like state dependent speed. And that's reflected in the bulk by the fact that the causal structure of space-time depends on what state you're in.
But in some sense, but still you somehow define, in the end, you can define speed as, how should I say, the averaging in a sense. Rather than, if you can really trace the speed of light in a very, tiny amount of time, then what you observe is the speed of light itself, which is fluctuating.
Yeah, I mean, I think I get the spirit of your question. I don't have anything, unfortunately, super useful to say, but let's just say that in my view, the issue of how to deal with fluctuations in the bulk, like fluctuations of the geometry, and how to think about different speeds there, and how that relates to the boundary notions, I think is still, in my mind, unclear. So we don't fully understand that.
Okay.
So this is kind of a classical bulk picture where we just have a fixed space-time and we're not considering fluctuations.
Thank you very much.
Yes.
Chris, go ahead.
Yeah, thank you. Thank you very much. It was very exciting to follow your talk. So I have two very simple questions. One is about it's more about what do you know, or what as a community, about two things. One is the state of the degrees of freedom inside the black hole. So is it like, or is the horizon of the black hole in a sense a discontinuity where inside it's a thermal state and outside it can be something else, or is it more complex? So I didn't get really exactly the details of that. And then the other question is more what you mentioned right in the end in your conclusion. I was also not sure what is the relevance of this holographic principle for the real universe. In a sense, is there a chance that it has some practical implication for the world we live in?
Yeah, great questions. So let me take the first one first. So yeah, inside the horizon is very interesting. I would say it's not discontinuity so much as a change in the character. So what does falling into the black hole kind of mean from the boundary point of view? It means that you've thrown some information into this chaotic quantum system, and it's become so scrambled up that you cannot extract it with any simple experiment. Okay. That's kind of why information doesn't come out of the black hole. It's not impossible to get information out. It's just in some sense hard, or does not occur naturally. So you may have heard before the statement that the black hole horizon is like requires knowing the whole future. Like you need to know the whole future of the space-time to figure out where the horizon is. So it's really like, it's a saying, if you take your quantum state and your quantum system and you don't do anything crazy to it, then you'll never be able to get the information out for any reasonable amount of time. Okay, there may be some Poincare recurrence after exponentially long time, but we don't think the gravity knows about that. So that's really what's happening kind of that's one interpretation of the inside. Information inside is just information that you can't get out by any simple mechanism. No matter how you couple to the system, you'll never be able to read that information out. This is reflected in another property of the interior, which is that it grows with time. Actually, if you look inside the black hole, you can see it from this point. You can see here time is kind of going up, but actually inside the black hole, time points towards the singularity. So now there's this kind of long distance, like what was previously time is now like space. And this space grows with outside time in some precise sense. And this growth with time of this space is actually related to the growth and complexity, we think, of the quantum state. So the quantum state, you perturb it, it thermalizes, it looks like an equilibrium state, but it's still a pure quantum state evolving in this complicated Hilbert space, and it just keeps getting more and more complicated. And that we think is related to the growth of this interior. So we do have a quite precise picture. It's still conjectural, of course, but there's a pretty precise picture of what the meaning of the interior is and how to think about it in terms of the information content on the boundary. In terms of holographic principle and for our universe, it's still true that black holes have entropy proportional to their area, not their volume, even in flat space. So holographic ideas, started in flat space, and that was the place they began. So at least at the level of theory, we feel like holography should have some role to play. We don't know exactly how to formulate that holographic description, but many people in the community suspect that holography has some role to play there. But yeah, the big question is, how do we need to modify things, or what's different and what's new when you take these ideas? And yeah, I can't give you a succinct answer to that question at this point. But there are many calculations you can do for sort of more realistic black holes that nevertheless seem to capture aspects of this quantum information story that I've told you here. So we don't have the complete picture, but there is hope, I would say.
Thank you.
I think next is Francis.
Sure. So thanks for the talk.
Thanks.
So this might be an ill-defined question, but so you talked closer to the beginning of the talk of this idea of space-time sort of emerging from entanglement, right? And so then later it looks like we're still in some of these formulas talking about things like distances and velocities, right? So are we to understand these now in terms of these entanglement relations?
Yeah, that's right. I didn't emphasize this overly much, but what's happening, let's see, what's a good picture? Yeah, I mean, this kind of picture here, where most of our understanding comes from a limit of this theory where the geometry is weakly fluctuating. So on the boundary, you have an absolute notion of space and time. And in the bulk, you have some state-dependent notion, which in principle can fluctuate. But we're working in a regime where the fluctuations are weak. So the bulk space-time structure depends on the state, but the fluctuations around that sort of average value, if you like, are weak. And so it's partly a game in this limit of matching the dynamics on the boundary around some perturbations or whatever to the dynamics on top of a fixed background geometry in the bulk. So that background geometry depends on the state, but once you fix that state and you do some small perturbations on top of it, then the geometry is not changing too much. Of course, we can study back reaction, and that's something you can do, but the pictures I was presenting here are simpler in this way. So like from this point of view, we're not letting this particle back react here, right? And if the particle back reacts, so if it in principle has a mass and it deforms the geometry itself, and that's something you can try to calculate, and that will change the way that this relationship here works to some extent, right? And there are phenomena on the boundary that are sensitive to this. But yes, you should understand these different bulk speeds. As I said in response to one of the earlier questions, like the reason why the causal structure is different in the bulk is in some sense from the boundary point of view because the speed of information propagation depends on the state. Depends on whether there's other stuff there that slows down your entanglement spreading or not. And that's manifested in the bulk in this way.
So on the boundary, we still can't totally get rid of ideas about space. Like along the boundary, we still need to think about space and time in absolute terms.
That's right. You know, you can try to go further. So we can. I presented the easiest case here. We can generate more emergent directions, maybe even emergent time, in various ways from simpler boundary models. But yeah, here we have a lot of sort of a skeleton to work with, a superstructure on the outside of a rigid space-time at the edge, and then we kind of have a dynamical space-time in the interior. But you can try to take away some of that skeleton, some of that structure, and emerge more of the bulk from the point of view of the boundary. And that's something that we're thinking about among other people, but it's a challenging topic.
Yeah, thank you very much.
Yeah.
So I think Vincenzo is next.
So thank you very much. Beautiful talk. I have a quite general question, but perhaps I guess you can give a very sharp answer, because you start with the idea of the entanglement / complexity frontier, but then you talk all the way through your talk about entanglement. So my question is, why choose entanglement as the relevant feature? I mean, we know recently from many works in quantum information and in quantum information related to quantum physics that entanglement is not perhaps the best measure of the features of physical states. We know that probably the notion of computational complexity is more aligned to the way physical states behave, because we know that there are some things that are highly entangled but trivially computable, so trivially treatable, and on the opposite there are things that are barely entangled but very heavily complex. So there is this idea that complexity is replacing the notion of entanglement as a less orthogonal feature to express the actual complexity of physical states. So is there a link to this concept in this theory that you are presenting?
Yeah, that's a great question. In terms of why we speak about entanglement, there are a couple of reasons. I think it's mostly historical, like it was the first thing we understood, and then it became kind of just a phrase people use to refer to the whole set of ideas that people are thinking about. But to give you some more precise connections, like for these black holes, for example, if you wait long enough, like if you consider that black hole formed by collapse and you wait long enough, it looks like a thermal equilibrium state. And so none of the entanglement is changing with time. It's all essentially fixed, but the complexity is still growing. And that's reflected in that certain feature of the geometry that continues to grow even at very late time, even though all these surfaces, these Ryutakyanagi surfaces are just fixed, right? They don't change anymore. So there are aspects of the geometry that continue to change, and we think those are related to complexity. There's also connections to error correction. So like understanding how would you, suppose instead of letting this particle fall in, you wanted to make the particle instantaneously deep inside. That's actually, we think, a very complex operation to do. And we have some precise measures of how that's complex. And so yeah, there is sort of entanglement is just the start of the story. And actually now we think in terms of, particular patterns of entanglement, like patterns of entanglement that support quantum error correction or growth of complexity. So I think there's still much to learn about this, and you're mentioning states that have high entanglement and low complexity. So one of the simplest models of the entanglement structure of these things is just stabilizer states.
Yeah, exactly. That's what I had in mind, that they are trivially computable, although they are strongly entangled. That's
right. So from in certain kinds of contexts, the entanglement can look at a very crude level like pretty stabilizer-like. It's not, it's maybe mostly bipartite. there's very like, if you have three parties in a stabilizer state, it's all bipartite Bell pairs or GHZ, and it's very little GHZ. So, it has a pretty simple structure.
Okay.
But that's definitely, we know it's not capturing all the richness. So a lot of work nowadays is trying to understand and characterize more carefully, what kind of entanglement you have and how it relates to these more complete notions of complexity and related things.
Mm-hmm.
So people in the field are aware of this and thinking about it, but it's still common just to talk about entanglement as a way in.
Thank you very much.
Yeah.
Ricardo.
But my question is perhaps not so relevant. So when you answered Francis's question, you said that gravity, the metric in the bulk fluctuates weakly, little. This is the case, in the examples of ADS-FT that we know where n is large, the TOF parameter is large, but the cases that you can, you have ideas of producing systems in the lab that somehow mimic all these ideas, but the corresponding gravity would be strongly coupled, right? It would be having the Newton constant and the curvature scales all coinciding. Am I getting something completely wrong here?
No, we could imagine in the distant future to simulate n equals 4 super Yang mills or something. Okay. That's not impossible, but it's certainly more complicated.
You mean by this lattice gauge, analog?
Yeah, for example, if you have complete control, to be clear, no one's worked out the details of this, but I am not aware of any fundamental obstruction to, if you have a million, trillion, billion qubits and you can do whatever you want with them. I think you can, I see no obstruction to engineering, some large N SU engaged theory and studying its dynamics. It would be very complex, but not in any, as far as I know, any fundamental obstruction to that.
I see. In fact, I want to ask you a question concerning that, because I've heard some talks about this mimicking. Sorry, it goes off but since you raised it. So, okay, I see they're using the rotational symmetry, SU2, then this is upgraded to gauge symmetry. So it looks like gauge symmetry is a sort of accidental symmetry, but then it will not be exact. So there will be additional degrees of freedom than the pure Yang mill. So you see, because gauge symmetry is just redundancy, right? While in this construction, in the concrete cases, it seems to me that there is more stuff than just the minimal gauge theory they're simulating, or maybe I'm really missing the point. Have you looked into that, or?
Yeah, so so what you can try to do, there's various ways to approach this. So one approach, which is sort of, this is an important issue, as you say. One approach is a kind of condensed matter approach. Is in the condensed matter community, we actually have a lot of experience thinking about spin models in terms of emergent gauge theories. Like there are phases of matter where the simple description in terms of some gauge theory. So, and the gauge constraint is exact there. It's just that it's a rewriting of the Hilbert space in some way.
Okay.
Another way from the point of view of quantum computing, which is somewhat aligned in spirit, is to say, well, let me try to simulate directly the gauge invariant observables. So I'm not trying to formulate, I'm happy to formulate in terms of.
Okay, you just write in terms of gauge invariant, okay.
Yeah, it's complicated, but that's fine. I allow long range interactions, I allow whatever you want, but I work with gauge invariant observables.
Okay, thank you. Yeah.
And the third possibility, which I'll just mention, is that you can allow in principle small corrections, like you can allow gauge non-invariance. So for example, Juan Moldacena and Alexei Millikan recently wrote a paper a couple of years ago looking at like BFSS matrix model, where they allow open strings, which is like allowing some gauge non-invariant operators. And they argued that actually these open strings kind of stay near the edge of the space and don't get close to the black hole. And so actually they're not modifying the physics sort of in the deep infrared that much. I don't make a general claim. I'm just saying like, this is something that the community can think about. And it's not obvious that at strong coupling, especially, that gauge symmetry breaking is a like killer, that you can't deal with it.
Okay, I see, thanks.
Yeah.
Okay, so it's 5:30. If there are no further questions, let's just thank Brian again for this inspiring talk.
Yeah, really inspiring. Thank you.
Thank you. Thank you.
Very much.